The most significant rise in energy demand is expected to come from developing countries, where growing urbanization would necessitate the development of large-scale electrical producing facilities. New energy sources must be created in order to meet environmental criteria for zero or low CO2 emission sources, as well as the necessity to invest in a sustainable energy portfolio. It is expected that fusion will be available as a future energy alternative by the middle of this century, and that it will be able to play an important part in delivering a sustainable, secure and safe solution to meet European and global energy demands in the future. Fusion is the mechanism that generates the energy that powers the sun and the stars. All life on Earth is made possible by the presence of energy. It is referred to as fusion because the energy is produced by fusing together light atoms, such as hydrogen, at the extraordinarily high pressures and temperatures seen at the Sun's core, 15 million degrees Celsius. Fusion is also referred to as fusion reaction. When exposed to the tremendous temperatures experienced in the Sun, any gas transforms into plasma, which is the fourth state of matter, with the other three states being solid, liquid, and gaseous. When it comes to atoms, plasma can be described as an electrically charged gas, in which the negatively charged electrons are fully isolated from the positively charged atomic nuclei by the positively charged atomic nuclei, or ions. Despite the fact that plasma is only rarely encountered on Earth, it is estimated that plasma accounts for more than 99% of the universe's total volume. Fusion power is a theorized kind of energy generation in which energy will be generated by employing nuclear fusion reactions to produce heat for the generation of electricity. Fusion power has the potential to be used in a variety of applications. The process of nuclear fusion occurs when two lighter atomic nuclei unite to form a heavier nucleus, while also releasing energy in the process. This is the same process that provides energy to stars such as the Sun. Fusion reactors are devices that are specifically intended to harness this energy. With the reduction of CO2 emissions driving future energy policy, fusion can begin market penetration around 2050, producing up to 30% of total electricity production. It is expected to contribute significantly to baseload generation by 2100, and to contribute significantly to renewable energy by 2050. When gases are heated to extremely high temperatures, about 150 million degrees Celsius, atoms become totally ionized, and this process can be replicated on Earth. It is called a nuclear reaction. A process known as fusion occurs when the nuclei of light atoms such as hydrogen, consisting of one proton and one neutron, fuse together to form a new nucleus, releasing energy. The center of the Sun has a natural fusion reactor. Before the Sun formed, it was a cloud of gas primarily composed of hydrogen with a small amount of helium. Eventually, the cloud grew to such a gigantic size that gravity forced it to collapse inwards upon itself. Multiple collisions in the Sun's core at that point released electrons from atoms, forming plasma, and leaving behind nuclei known as ions. A star was formed when contact between ions became so frequent that they became near enough to fuse, causing the ball of gas to ignite and burst into flames. Researchers on the planet Earth are attempting to create their own fusion reactors. They are attempting to maximize the number of ions in a limited location, as well as the period of time that they are able to remain in close proximity. In order to accomplish this, fusion reactors heat plasmas to temperatures that are hundreds of millions of degrees Celsius higher than the core of the Sun. Strong magnetic fields or high-powered lasers are then used to restrict the plasma into small manageable zones where fusion can take place, as shown in the diagram. PPPL, as well as numerous other labs, universities, and commercial organizations across the world, are researching and developing the process of designing and optimizing these fusion reactors, as well as the technology that will turn the fusion energy into useful electricity. Tokamaks, such as the National Spherical Torus Experiment Upgrade, NSTXU, at PPPL, are donut-shaped facilities that pump the majority of the extracted energy into fast neutrons. In order to gather the energy from these neutrons, a blanket consisting of a molten mixture of lithium and lead that surrounds the plasma can be constructed. It will be possible to harness the excess heat in this blanket to create steam that will drive turbines and generate power. The main characteristics of fusion: an infinite supply of fuel and a high power density. would make it possible to produce carbon-free energy on the scale required to combat climate change. Making clean, safe, and cost-effective fusion energy available to our civilization is a major problem for science and engineering in the 21st century. There is no known science that prevents us from generating fusion energy. In fact, the essential conditions required to make fusion, such as reaching temperatures of 100 million degrees Fahrenheit, have been mainly attained, including in laboratories at the Massachusetts Institute of Technology. Many individuals, however, are skeptical that fusion will be available in a timely manner, given that it has been long promised, but has been slow to become a reality. Fusion has been delayed due to the fact that its science is more complex than originally anticipated, as well as the huge scale of experimental facilities required to investigate fusion. Utilizing newly accessible technology and knowledge, on the other hand, can help to accelerate the development of fusion energy. Many new technologies, such as high-temperature superconductors and 3D printing, are opening up exciting new possibilities for the construction of small fusion devices, while fundamental understanding of fusion science is being gained through advanced computing and measurement techniques, resulting in greater certainty about the operation of nuclear power plants and fusion reactors. Our fusion energy mission is centered on bringing these new prospects together in an integrated manner while simultaneously training a new generation of fusion scientists. It is the electrical repulsive force, known as the Coulomb force, that acts between two positively charged nuclei that prevents fusion processes from taking place. In order for fusion to occur, the two nuclei must approach each other at a high rate in order to overcome their electrical repulsion and achieve a sufficiently small separation, less than 1/1,000,000th of a centimeter, so that the short-range strong force takes precedence over the long-range weak force. A huge number of nuclei must undergo fusion in order to produce useful amounts of energy. That is, a gas of fusing nuclei must be produced in order to provide good amounts of energy. When a gas is heated to exceptionally high temperatures, the average nucleus possesses enough kinetic energy to undergo fusion on its own. An ordinary gas can be converted into a superconducting medium by heating it above the temperature at which electrons are thrown loose from their atoms. As a result, an ionized gas is formed, which contains free negative electrons and positively charged nuclei. This ionized gas is in the plasma state, which is the fourth state of matter in the periodic table. The majority of the matter in the cosmos exists in a state of plasma. The plasma at the heart of experimental fusion reactors has a temperature of over 1 million degrees Celsius. Fusion takes place between the nuclei, with the electrons there simply to keep the macroscopic charge neutrality of the system maintained. The temperature of the plasma is approximately 100 million kelvins, K, approximately 100 million degrees Celsius, or 180 million degrees Fahrenheit, which is more than 6 times the temperature of the Sun's core. Higher temperatures are required in fusion reactors because of the lower pressures and densities that are encountered. The loss of energy in a plasma occurs through processes like as radiation, conduction, and convection. Therefore, in order to maintain a heated plasma, fusion reactions must contribute enough energy to compensate for the energy losses. When a plasma's density and energy confinement time, the time it takes for the plasma to lose its energy if left unrelated, are multiplied together, they must surpass a critical number in order to achieve this state of equilibrium.